Hello and welcome to our paper presentation, to our paper, A Concept for Highly Automated Pre-Labeling via Cross-Domain Label Transfer for the Perception in Autonomous Driving. My name is Maarten Bieshaar, and this is joint work of my colleagues Marek Herde, Denis Huseljic and Bernhard. So what's the idea? What's the motivation? As the title already states, it is about perception in autonomous driving. And if we are dealing with autonomously driving cars, we are facing sensors like cameras, LiDAR, radar, and so on. And well, as technology is evolving, as well, computers are getting more powerful, it seems in the last years that machine learning is really the enabling technology for perception in autonomous driving. So if you're doing a good job regarding machine learning, you are most likely to be very successful regarding the perception in autonomous driving. And you see this trend if you take a look at the big car manufacturers like Tesla, who's putting a lot of effort in AI and machine learning in particular. So to be successful in machine learning, to successfully build a perception module for autonomous driving is, well, you need a lot of training data. But not only training data, you also need high quality labels. So if you have bad quality labels, for example, here on this on the bottom you see an example of a camera, and you see annotated boxes of pedestrians and cars and so on. And if these are bad, your AI or machine learning model won't learn anything useful. It might be even misleading if you put a lot of data with bad quality labels in there. And it's not only about training, it's also about, validation of your learned models. So training and validation of these machine learning models requires a huge amount of high quality labels. So to get these high quality labels, that's an expensive process. And we searching for, I mean, that's one of the purposes of this workshop, searching for methods to reduce the cost while getting more labels and better quality labels. And in autonomous driving, I already said that you're facing different kinds of sensors. Here on the right-hand side, you see, for example, a LiDAR sensor. And the idea now of our proposal, of our concept, which we are working on right now, is that we want to exploit the sensor diversity. So the sensors have different strengths and weaknesses. Here on the right-hand side, you see a car as it was used to record the famous news scenes data set. And on the left-hand side, you see, a table which shows different strengths and weaknesses of different sensor modalities. For example, a camera might have a good angular resolution, whereas if it's dark, so the environment is bad, you won't see anything, and it's better to pay attention to your LiDAR or radar or whatsoever. And we want to exploit this diversity. And the idea is now that we create pre-labels using different sensors. So we have a model which we can use to detect object in camera images, and we have one which for LiDAR. And we want to use these labels. If you have a model which is pretty sure on camera, we want to transfer this kind of pre-label, this very safe detections to another sensor modality, given that we know the parameterization, given that we know the calibration. And then one very interesting aspect is that we want to include methods of interactive learning to estimate the quality of these transferred labels, of these kind of, it's not really labels, it's a kind of pre-labels as we termed. And that's really a novelty. I mean, the other thing, it's kind of more like this sensor fusion stuff, which is in the which is in car manufacturers for decades, in robotics and so on. And now we want to, additionally include this interactive learning part in form of a label quality estimation. Let's come to our proposed concept. Assume we have the task of detecting objects in camera images or in LiDAR scan. So we're considering camera and LiDAR, and the task is to detect objects, meaning to classify the objects in an image or in a LiDAR scan, to determine their position in 3D coordinates, to determine their orientation, and to determine the bounding box, well, the dimension of the bounding box around that particular object. In the first stage, we're using probabilistic object detectors for detecting objects. And we're using state-of-the-art algorithms such as the center-net approach for that. And, well, what does that actually do is, well, we detect objects, we predict probabilistic class labels, so we're having categorical distribution over the class labels for a dedicated object. And we are extending this idea, which to also a more generalized probabilistic object detection, in a sense that we also predict probability distributions over the location and the dimensions of a particular object. In a second stage, we ensure that the probabilities which we obtain from the first stage are valid, meaning we calibrate them. What that means in detail, I'll explain later on. Then we transfer the labels from the camera image to the LiDAR scan, or vice versa, depends. And we can, given that we have well-calibrated predictions, we say, okay, with a certain probability, say a threshold of 90%, we transfer all labels where we are pretty sure that they are correct into a pre-labeled data set, and we are then later on using this to, for example, retrain our model. Whereas in the third stage, which is kind of optional, we could also fuse information originating from the camera and the LiDAR and use the fused information to form a pre-labeled data set and kind of transferring this knowledge back to the camera frame or back to the LiDAR frame. In the fourth stage, and that's a really important stage and kind of one of the innovation of our concept, is that we include a labeling quality assessment module. Essentially, the main idea behind that is to kind of put a quality sign on labels, saying that we, for example, have an automatically labeled data set, and we are pretty sure, for example, you can say our estimated mean average precision value of these labels is, for example, say 80%, something like that. And we ensure this by a label quality assessment. So we make predictions about the label quality of the pre-labeled data set, and we kind of support this by a human-in-the-loop learning, for example, using active learning techniques and so on. Then, after we have a certain threshold on the label quality, and we've ensured that, then everything is put into a labeled data set, which then can be used to close the loop, meaning to make our probabilistic object detectors better and to ensure better probability calibration by retraining. So the first stage, as I already said, it's about probabilistic object detection. How does that look like? On the left-hand side, you have an image. You have your object detector, which is, for example, the center-net approach or YOLO or whatsoever, and then you output bounding box prediction. That's typical as in the upper part of the slide, and you also put a kind of a probability assigned to that. And a probabilistic object detector, here it's all about 2D boxes. Actually, we are aiming at 3D boxes, but for the ease of simplicity, we depicted only 2D boxes here. We are aiming for probabilistic object detections, so we are aiming for a categorical distribution over the classes. And we are aiming for a Gaussian distribution to model the bounding box uncertainty. Moreover, we separate between the aleatoric and the epistemic uncertainty. And, a high aleatoric uncertainty means that we cannot distinguish, certain objects which are ambiguous. And we cannot say, okay, that's on the left-hand side, that's dedicated as the car. But it might also be kind of a truck or whatsoever, or it might be a cycle, a bicycle. I'm not sure. That's something which is then more the ambiguity of an object, which refers to the high aleatoric uncertainty, where we really can't say what it is. On the other hand side, we have the epistemic uncertainty, which is something which you haven't seen before because you haven't encountered that in your training data. That may, for example, be a ghost like depicted here. And our probabilistic object detectors also aim at making this distinction between high aleatoric uncertainty and high epistemic uncertainty, which we later on then use for label quality estimation. Second stage is the probability calibration. So it's really about making sure that your probabilities are valid. And you see it here on the left-hand side, where we plot the confidence against accuracy. And a well-calibrated model should be really along the, black dotted line. And it's a very important aspect for reliable decision-making. In the third stage, which was kind of optional, we first investigate CameratoLighter Transform. So we start with bounding boxes in the camera frame. We transfer these bounding boxes to a pre-labeled LiDAR point cloud. So we transfer them directly, given that we know the camera, the extrinsic parameters. Then we additionally refine the bounding boxes using the LiDAR points, for example, using an ICP, iterative closest point algorithm. And then we output the refined pre-labeled LiDAR point cloud. We can also do it the other way around. So we start with a LiDAR point cloud, we transfer it to a pre-labeled camera image, and we refine the bounding boxes and output a refined pre-labeled camera image. The third approach is that we kind of fuse both together. So we have detections in the camera frame, we have detections in the LiDAR scan, we fuse them together, for example, using a common state space, which is dedicated or given by the position, orientation, or dimensions of the bounding box and the class. We have to cope with the matching problem using, for example, the Hungarian algorithm. And then we could, for example, using Bayes' law to fuse the predictions from originating from the camera and the LiDAR. Problem here is that we are facing, sensor miscalibration and bad timings. So one sensor may be more accurate than the other. The fourth opportunity is to also include temporal dimensions, the temporal dependencies, via tracking by detection, using, for example, a Bayesian state space filter such as the Kalman filter. In the fourth stage, we are dealing with labeling quality assessment. So we want to say, okay, that's on the left-hand side, for example, that's a good bounding box annotation. Whereas in the middle, we're seeing a ghost, so we are very unsure about that, so we cannot make a really assuring prediction about that. So that would be a bad quality. And on the right-hand side, it's something, we don't know, so it's kind of labeling quality is I don't know. And aspects which we have to consider is the out-of-distribution detection, which refers to the ghosting, for example, there above. So what about the uncertainty regarding the bounding box predictions or the distribution about object categories, because we're just not sure what the object really is. And then we integrate that into an interactive learning cycles where we have images or LiDAR scans with predictions. We select certain from that in an intelligent fashion using, for example, active learning strategies. We give them to annotators to let them correct these images and put these images with corrected predictions in there, retrain the object detector and go along until a certain criteria, stopping criteria, is reached. So let's come to the conclusion and possible extensions. So we proposed the concept for highly automated labeling in automated driving. We distinct the aleatoric and epistemic uncertainty for object detection, and we propose a mechanism for putting quality seals for automatically generated labels as starting point for interactive learning. As this is the concept, we are really happy to learn about your input and your ideas on that, and currently we are really working towards the realization of that concept. Possible extensions are, extending this idea to different sensor and application domains, let's say more general in agriculture or robotics, to include this continual learning aspect, or the more tight integration with semi-supervised learning. So thanks for your attention, and we are happy to take your questions.